Awesome. So thank you guys for joining me every day for this stuff. Okay, so good. So last time, let's see where we were at last time. We had the following. So the very last time we were showing that there was a soft theorem, word identity equivalence. And this word identity was for asymptotic symmetries. And then we also kind of left off this teaser that word identity soft theorem was equivalent to also a 2D word identity for occurrence. So in particular, this TZZ example. So TZZ, the stress tensor, was corresponding to super rotations. So I look up this time, make sure it's right. And then that was equivalent to the subleading soft graviton theorem. So the nice thing about that was essentially each of these examples we were pointing out were kind of brand new. This was from, say, 2014. This was proposed maybe 2011 or so by Barnett and others. And now we have this candidate 2D stress tensor, which really motivates us going to look at scattering in a manner that makes each of the external states conformal primaries in this celestial CFT. So this type of set of connections, especially here, and then also some memory effects, is something that you see across different gauge theories. And also you can even extend it to like scalars that are related, I think, like via double copy, or also supersymmetric multiplets, like there's a soft Fotino theorem also. So this set of connections is quite universal. So you can look at not just this example here. So we also have currents for Kac-Moody symmetry coming from gauge theories in the bulk. Similarly, other currents you can define here. So essentially, the reason why I pointed out or spent most time on this one particular example of superrotations in the subleading soft graviton is because this stress tensor is not only something nice from the point of view of motivating a celestial CFT, but also motivates the map that we want to do next. So what we want to do is we want to take our S matrix and we want to map it to a set of correlators. And so the way that one wants to do that is essentially we're going to have each of the external states mapping to these local operators. And from the point of view of okay, so I'm going to, what I have to do today is basically motivate how this map actually works. But in principle, just counting the number of degrees of freedom, just to remind ourselves, if we have a massless out state, for instance, or in state, there's a certain direction in which that momentum is pointing. So that will be isomorphic to this point on the celestial sphere. And then we also have some helicity of these particles that will be the same or negative of this J index here. And then we also have an energy, and that energy is going to be traded for this delta. So just as far as counting the number of independent variables, it matches. And also from the point of view of Lorentz invariance here, that's how we get this global conformal invariance here. And we're going to show explicitly how to construct that. That's the first thing we're going to do. So the reason why we are now able to do this after kind of spending this time on this soft theorem stuff is that essentially the stress tensor here will only give you definite values of the weights if instead of in the standard momentum basis, we went to a boost basis. So what we're going to need to do, so essentially TZZ candidate is telling us that we need to go to boost eigenstates. Great. So now I'm going to start from an abstract construction for the external states here that will guarantee this correct transformation properties of this mapped S matrix elements. And then those objects are called celestial amplitudes. And then we're going to start exploring properties of celestial amplitudes. So the very first step is just to make sure that we understand this map. And I'm going to define the map in a more general context so that like in practice, when we're talking about massless scattering, there's a kind of quick and dirty way to get from amplitudes to celestial amplitudes, which is going to be this Mellin transform in the energies. But I think it's slightly nicer to be more formal and show that this covariance is guaranteed and work through it that way. So the first thing I'm going to do is I'm going to define a conformal primary wave function. So definition, a conformal primary wave function is going to be a wave function that is going to depend on the bulk space time, also a reference direction, and I'm going to transform in a certain way. So the full definition is written out in the notes, and I'm going to hopefully be able to write and talk enough that it's not too slow here. Normally, wave function is a function. So first of all, it would be R1, 3 or R1, D plus 1. And it transforms with like definite SL to C weights as follows. So as a wave function, it's the function R1, 3, but also has a dependence on a reference direction. So we're going to see that here. Good. So I'm going to do some boost of my space-time, and at the same time, I'm going to transform the reference direction. So you notice that in the first lecture, I was talking about how if I embedded this W plane into R1, 3, that I could show that the Lorentz transformations were isomorphic to those transformations. So here, I am not, I'm letting W be an abstract, like independent coordinate that I'm like, it's not embedded in this X value, but because of the isomorphism of the transformation, they're both going to transform the same way. And so the lambda that I wrote down before is going to be the same one here. But technically one could do a relative SL2C transformation before you define that frame, but that's going to be irrelevant. So this bar over C bar, and this is how we want it to transform.
Sorry, it's not updating.
Oh, it's not updating? Okay, good. Okay, Lisa's like, thank you for catching it. Oh my God, thanks, Siri. So let's see what I can do to make it magically appear. So I write really fast there. Great. So awesome.
Thanks.
Thank you for catching that. Please do that again if that happens. So times phi as delta J, the original variable. So I don't think I need to write that. Yeah. So So okay, good. So essentially what's happening here, right? So I'm kind of putting the transformations on one side. We can also move this to the left-hand side and just say that there's a certain covariance property here. And so this is just the definition for this guy. From the point of view of the external scattering states, so if I want to like prepare a like scattering state, then I'm going to make this guy satisfy the appropriate EOM. Right, so what that'll amount to is essentially, at the moment, I've let myself have this arbitrary spin S representation, not tied the value of J to S. But what I can do is essentially, if I'm looking at massless scattering, then the fact that I am only going to look at the spin equal to the helicity is going to remove like longitudinal modes. And then, but for the massive case, obviously you can have like basically different projections of the massive polarizations on the celestial sphere. So you're going to have right now the value of the S equal to J for the radiative stuff. That's going to be a solution to the equation of motion. And then what we're going to see is that if we have a guy that does solve the equations of motion, then we can do the same construction that we're going to do when one starts with the LOC formulation, which is I want to select the creation and annihilation operators by taking inner product of my field operator with the appropriate wave function. So in this case, if I have a local bulk operator, and especially if I know it as terms of a function, sorry, let me just write down the expression, and then we're going to talk a little bit about what I mean by it. So there are a couple caveats when one thinks about the fact that this construction is supposed to eventually talk about the theory of quantum gravity. So maybe you don't have these local bulk operators, but that's where our first lecture will come into play. So here I'm just defining this guy. So let me write this down. Sorry. This is a nice way to, okay. So let me just make sure that I'm clear on my notation here. So the first thing that I have here is I have an inner product on solutions to the appropriate free wave equations. So this would be the Klein-Gordon inner product for spin 0, and then like Strunkoff-Witten, or like, I'm sorry, I'm like trying to think of the best reference, but essentially there's a standard inner product for spin 1 and spin 2 that I also wrote down in the notes, and that's what you're using here. So what that would do is it would take any in this guy, so this guy is the local operator in the bulk, and typically we think of this and as like this mode expansion of the like creation and annihilation operators times the appropriate plane waves. And I also think I wrote that down, hopefully. So when I have that guy and then I put like a plane wave here, I will basically be selecting out the creation annihilation operator here. So the thing that I'm doing now is essentially I'm changing my external wave function, but I can still use the mode expansion for the standard momentum states. And so if I do that, so if I don't try to change how I expand this operator, then this gives you a nice way to see how this total definition of this guy that I'm creating is a function of the creation annihilation operator. So this, you would see that this guy is essentially a Mellin transform of the creation annihilation operators for the momentum space ones, but I'm previewing that ahead of them. So I guess that's more a statement to people who know that. For the moment right now, all I'm saying is that I need an operator in the bulk, I need an inner product, and I need a solution to the corresponding wave equation. And that would give me some operator here. And because of the way that I've defined this to transform, I have an operator that's going to transform like a local operator in the 2D CFT. And I think I'm going to show a couple steps to make sure that we know that that's the case. So the important thing to keep in mind is, okay, so when we're doing this construction, eventually we want to think about the fact that we're trying to set up a holographic description to describe quantum gravity in the book. So part of the power of what we were talking about last time was that we were talking about asymptotic symmetries. And we've showed a word identity using, like, for instance, I think even just like trivial amplitudes for like the to not worry about loop corrections to the stress tensor. But you can show that at loop order, you have loop one of exact corrections, you still have this word identity. So what Wynn has done in that case is basically a semi-classical version of a word identity. So you really only proved it using perturbation theory, treating the metric like it's a quantum field. And that's all fine, but then the fact that I want to say that that's a symmetry of quantum gravity is a bit of a jump. And it is supposed to be a jump in the sense that we're saying we're putting those symmetries first. So if you then say, okay, I want my word identity to hold in the full quantum gravity theory, that's the stronger statement that you can make. And one can look at like examples of the Hawking-Perry-Strominger papers where they're trying to take that word identity and push it to interesting statements about black holes and like the behavior at the horizon. So that is the attitude that we have in mind. So with that in mind, when I am writing down this expression in terms of this bulk field operator, essentially I can always push this Cauchy surface up to future past null infinity, and then this guy is on the boundary. So it's a bit like an extrapolate dictionary in normal ADS CFT. But now the boundary is null, so take that as you will. Great. Okay. So with this in mind, and it's also, so essentially there too, like, so the alternative in the momentum space picture is if I put a plane wave in here, then this guy is now going to select out the creation annihilation operators. And so essentially what I'm doing is I am, by pushing my Cauchy slice up to future null infinity, what I had is what I told you with the saddle point approximation. I had basically what turned into the direction of the momentum. So p hat was parallel to x hat. And then I still was left with the integral over u. So what the starting point of the LSD formulation is the same, where basically I am trying to take some correlation function of time ordered operators here. And then I take an inner product with these wave functions. And then when one Fourier transforms that time ordered correlator, one shows that you basically end up putting the creation annihilation operators out like at the early and late times when you just take this inner product to be on the t equals negative infinity or plus infinity slice. So the funny thing about that, so that construction is nice because in the end, what one gets is after you Fourier transform, you can see that that contribution becomes the residues of poles as you take the momentum to go on shell. So the kind of funny thing about it, if you're maybe more of like, I want to talk about correlation functions, and the funny thing about it, so instead of LSD, like the final form of that LSD thing, if you started from just saying I want to act in the out vacuum with some A's and A daggers, so A dagger on in and A on out, prepare the in and out states, then what we can kind of see is that the S matrix is also just a correlation function of these integrated along the null infinity generators of the field operators. So it gives you a kind of correlation function version. And I think that's slightly nice because one doesn't have an S matrix in ADCFT in a similar way to the how like it's basically what I mean to say. The subtleties about that is essentially now if I'm talking about correlation functions, I can maybe not worry so much if this also is a conformal field theory here, et cetera. So I just I like that aspect of it, and I wanted to like rant a little bit about that. But what I'm saying here, like this will still be fine in theory of quantum gravity because I can always push it to the boundary. So that's my rant. And yeah, thank you. So okay, great. So now that my rant is over, I want to say how this definition right here is make sure that this object actually transforms the way that I want it to. So when I look at this definition, what do I actually have? So this representation here, essentially, so these fields are going to be like tensor fields or spinor fields on the bulk space-time. And so when I can think of this Lorentz transformation, and this part here is basically doing the Lie derivative along the x coordinate of these guys. And then if I look at this transformation in W in isolation, I can look at how this transforms for an infinitesimal guy. So what I'm saying is if I put everything on one side, so if I put all of this ds over here and the same thing there, what I end up getting is the following version of that. So essentially I have my Lorentz generators in the representation that is the position space guy, plus the Lorentz generators acting in the W coordinate. So I'm going to call it C, I guess is the closest cleanest notation here. Good. Okay. So what I'm saying is that basically this statement, the infinitesimal version, is equivalent to the representation of like the transformation in the x coordinate canceling the one in the W coordinate. So when I have this guy, then basically I can use this and then the Lorentz covariance or Lorentz invariance of this inner product to show that this transformation is here. So I'll show one step of it, but like the appendix of this paper with Emilio and Andrea goes into more detail on it. So essentially what I want to say is I have various representations of the Lorentz generators that are occurring. I have the one that's in W, I have the one that's in X, and I have the one that's acting on the Hilbert space. So all of these operators on my 4D Hilbert space will transform into the Hilbert space representation. So I'll use M sub H curly to denote that. So if I want to take my corresponding, this should be Hermitian because I'm using the 4D Hilbert space right now and seeing what inherits to my 2D guy. O hat S, the function of X. This commutator is basically going to be a Lie derivative. So on my operator. And again, this is all modulo gauge invariance. So keep that in mind here. If it's a scalar, everything is legit and fine. But when there is gauge invariance, then all of these are kind of quotient by gauge transformations. So this is what I have just from the fact that I have my local operator and my operator in my Hilbert space that induces the Lorentz transformation doing the appropriate kind of motion of the operator. So this is the covariance or the consistency of the representation of that local operator and the transformation in the Hilbert space. And then what this is going to imply is, okay, basically I can do that commutator on this quantity because this is just a, it's linear in this operator, and it's just an integral over the Cauchy slice of some function times that operator. And so what that'll end up telling me is that this guy is equivalent then to the same mu H acting on O S plus minus delta J is going to be just the change in C. And so by writing Lie derivatives out, I guess one could also just, I was a little bit shorthand with this notation here. Basically, there's two steps involved here. So this guy changes this operator as if it's just moving in the X direction here. This inner product is Lorentz invariant, so I can shift that X transformation here to the X transformation here. Then I'm using that this invariance basically equates the X transformation to the W transformation, and I get the W transformation here. So this Lie derivative, I guess, technically is acting on some sort of weighted function, so it's a little bit of a schematic there. But basically, what I'm saying is that you're guaranteed by construction to then have this object, which even though it's an operator in the 4D Hilbert space, transforms like a 2D quasi-primary. So you have that. So that's nice. And let's write this equation in a way that's a little bit more reminiscent of the 2D CFT. So what we have is we have L0. Oh, I'll write just down the L and not the L bars because it's going to be too much. Is 2W dW plus H of OH. And let me also, I'm going to be switching back and forth. So let me just say it once and for all here that H is going to be 1/2 delta plus J and H bar is going to be 1/2 delta minus J. And because they're isomorphic and I'm never going to like do any like light transforms or anything that's going to like screw with I guess the intuition for what values they take, I'll basically always write down H and H bar and delta and J interchangeably here. So I have this, and then I have L -1 O H H bar.
It's not updating again.
No, okay, thank you. Oh my God, brownie points to that. I feel like I don't know if anybody's grading the tutorials, but like whoever catches that like should get extra credit. Okay, so not that it matters. But maybe one of the banks that sponsors the secondary points things. So okay, reward things. Okay, so we have this guy, L plus O H H bar. Let me move everything. I love that I can move. My bad planning with these can be corrected easily. Okay, so let's move it to equals W squared dW. Okay, so okay, so now that we have the algebra, the nice thing to point out right now, so essentially the thing on the left-hand side right now is some complex combination of my generators of my symmetries in the 40 Hilbert space. Modulo the fact that okay, so I wrote them down before, so it's just some combinations of like the boosts and the rotations, so that the algebra of the Li matches what we want. We want it to match the weight algebra. So what I have now is essentially that action on my operator, and this operator is a function of W and W bar, turns into this transformation property. So in particular, taking descendants, so acting with a particular generator from the 40 Hilbert space is taking just a W derivative here. And this is going to be very useful for the way that I'm going to kind of construct the currents starting off, is just I can take derivatives here to do descendants. So just keep in mind that if I, like the thing that we're going to kind of advocate for is that the analog of like the state with a given H and H bar is going to be like taking this local operator to like the North Pole, say, if you wanted to do like radial quantization. So in that case, then W is 0, and essentially you just see the weight L0 of O there. And then this would be 0 because W is 0. So right now I have this by construction where they have an operator in the Hilbert space doing this. And then I have this differential relation for how I move things around because of the way that I've set up my wave functions. So it's all guaranteed from that. And so now what I want to do is basically, I've said that if I demand my wave functions have a certain covariance property, I will get the operators that I want. And also I can see that if I push those Cauchy slices up to future null infinity, that they are indeed preparing my initial and final states. So this is what I'm scattering. I want to now actually write down what those wave functions are, because it's better to maybe be less abstract. So let's see, like the ingredients for phi s delta j. Basically, I can take them as a product of some tetrad elements, some spinor elements, and some scalar wave function delta. And I'm going to construct what these objects are. So I can write a covariant tetrad that transforms with definite SL2C weights as follows. So I'll write down the full tetrad, but we're only going to ever use the guys that are spin 1. then M bar is basically the opposite of it. So with that in mind, basically what I have is essentially right now, this is my polarization vector. So this should be a plus polarization. This is minus polarization. And then this is now a space-time dependent polarization, essentially. You can see that if I shift epsilon by Q, this actually stays invariant because of the way it's constructed. But essentially these guys have the standard inner products for a orthonormal tetrad. So each of the vectors are individually null. These have a non-zero unit inner product, -1, and these have a unit inner product. But the point that I care about here is that essentially, if I do the simultaneous transformation where X gets mapped to lambda mu nu X nu, and W gets mapped to AW plus B over CW plus D, that these objects each have definite weight. So in this case, all of these guys have delta equals 0, and N, L have J equals 0. And then these guys have J equals +1 and J equals -1. Now I also have another further decomposition, which is good if anybody wants to do spinor stuff. So if I use the isomorphism that's in the first chapter of the lecture notes to go from the standard like 4-vector to bispinor, what I have is I have that L A B dot is an outer product of these O's. So all I'm saying is basically I can also construct a spin frame. So I'll write it up because it's not that weird to write. And then, okay, so the point here being that this OA is essentially I negative Q dot X to the 1/2 times the spinor. Basically, this is like the spinor helicity variable stripped of the energy. And then IA is basically as if you had this like twistor space incidence relation here, where it's dependent on the O. And essentially, so what happens here is this: so this guy has J equals +1/2, and this guy has J equals -1/2. And so, like, obviously, like the independent guys are this guy and its complex conjugate, which would be the angle bracket spinor. So what I want to point out is the following. So these, if I take the tensor product of these guys with then my scalar wave function, which is phi delta is negative, sorry, not negative, is just 1 over negative Q dot X to the delta. So one can check from the way that basically Q, when I did a Mobius transformation of the W coordinates, the reference direction got rescaled. So that's giving me the weight here. But otherwise it would be, if it were just a Lorentz 4-vector, this would be invariant if they both transform like Lorentz 4 vectors. So this guy gives me the weight. These guys shift the weight a little bit. So don't shift the weight, they shift the spin. So I get the spin from the tetrad and spin frame. I get the weight from the scalar. And I can also multiply by any function of X squared because X squared is invariant. So my general onsets is of the form, basically, if I wanted to have some spin plus N guy, I would take mu dot dot dot, right? So like mu1, mu2 up to mu s. Then I would take a function of X squared, and then I would take phi delta. And this guy would have, this would be my phi delta s plus s wave function. So up to mu up to mu s. Okay, so I have this guy, but when I said that I wanted to take an inner product and prepare an external state, this actually has to satisfy the equation of motion. So when I do that, what I find out is I basically, if everything turns into just a function, a constraint on this guy here for the radiative guys where J equals S. So I essentially have to find the function of X squared that will make this guy solve the appropriate equations of motion. And the equations of motion are also written down in the notes. And what we find is the following. So I'll just write down the spin 1 case for now. So if I wanted to look at A delta and then J equals +1, it would just be M by delta like I wrote there. And the same thing with A delta -1, it's M bar by delta. Now there's actually a second set of solutions. So right now delta can be in C. Second solution that I get for generic delta here is the following. A tilde delta then -1 is negative and then A tilde delta plus 1 is negative. So basically, the reason why I want to write down all these solutions, I want to point out that if I said, okay, so I'm going to have my 4D spin equal to my J, or equal to the absolute value of it. So I'm not fixing that right now. And then I want to look at solutions to the equations of motion. I basically land on only these options. And one can see that there's two options, where basically what happens is that the J can be plus or minus 1 in two different ways. And the funny thing about it basically is that these are actually not all linearly independent. So with Shuhong and Andy, we're studying these guys, and we, with Shuhong, found that like if you have scattering in the principal series basis, that's enough to capture the radiative states, for instance. Now, these guys are actually conformally shadowily related to the ones here. So if I wanted to construct a complete basis of the finite energy scattering states, then I'm only going to look at, say, either the Mellin transform modes, or these are the shadows of these guys. Okay, I'm going to free jump to a conclusion here. But basically, I only need one of these two sets, or some combination of them. So essentially what I'm going to look at right now is I don't need to include both of these. I can just include one of them and then study properties of that. And I can always do a S2 transform here. So it's just a convolution in the W coordinate to take me from these guys to this guys in the bulk. And I guess it's slightly cute to see that the position dependence changes here. And one way to see that is essentially, if you look at the fall offs of like the bulk to boundary propagator, you have a contact term and then you have a power law term, and the smearing essentially exchanges those two. So that's where in the bulk you have this change in the radial behavior here.
It might be frozen again.
Okay, okay. Luckily, even if it froze, all I was doing was basically like circling stuff on it. So hopefully there's nothing missed aside from where I was pointing while I was talking. So good. So what we have now is essentially, what I want to point out is we only need to look at these guys. And when we look at these guys, there's even a nicer thing about them, which is that they're basically in the same gauge equivalence class up to a normalization of just doing a frequency transform of the standard plane waves. So let's look at that. So the claim I have is the following, is that if I start with my scalar wave function, delta, there's a nice way to write it, which is as follows. Where this guy here is an integral from 0 to infinity of my energies of a plane wave. Okay, so I need a regulator to basically guarantee that's always damped for this guy to converge. And then what I have is essentially that this is just, so this is a Mellin transform from the energy of this plane wave. And the reason why I've stripped it out like this is because basically all of my other different spin guys would be this scalar wave function, which is the Mellin transform of the plane wave times like the polarization vector. So what I have is the following, is up to gauge equivalence. I have that A delta J is going to be gauge equivalent to some overall normalization factor over epsilon mu J phi. Okay, so there's a plus or minus regulator here because basically of the way that I needed to choose a phase for the damping. But what I want to point out is essentially, so these wave functions are nice. They were then, if you don't take a large R limit, they're never going to have like some zeros at special values of delta. So as far as the function of delta, like this looks nicer. But from the point of view of doing transforms of amplitudes, it's easier to start from the S matrix in momentum space and then do an integral of it. So want to point out that depending on your choice of normalization, like sometimes you want to group these factors into the definition of the operators or not. But the key point here is that basically, if I wanted to prepare a scattering state that is a conformal primary and it's a massless field, all I have to do is integrate over the frequencies. And if I look at how I constructed this guy, because I said that if this were the plane wave, this would just give me my creation annihilation operator. When I do that frequency integral here, then I can do it also here. And I'm basically just Mellin transforming my external states. So I can take my S matrix elements and literally do this transform on it for each of the particles. And then I land on my celestial amplitudes. So now we actually have kind of the punchline of this lead up, which is that my correlation functions And this is, I
It's
guess, how I
frozen.
define my celestial amplitude.
It's frozen
No,
again.
it's frozen again. Okay, I gotta like, yeah, figure out what I'm doing to make it happen so that I can just reveal on command. Okay, so I equals 1 to n of integral from 0 to infinity d omega I to the delta of I minus 1. Of my out. Okay, so this is very nice for for massless scattering. All I have to do is do a single integral over each of the external states, and I have my celestial amplitude. So practically speaking, you can say this is my celestial amplitude. So anything that you know about amplitudes, you say, how does it behave when you you integral transform over the energies and exchange that omega for a delta? That's how the celestial amplitude would behave. So from the point of view of given the fact that there is this kind of whole motivation for asymptotic symmetries and wanting to do this map, like then we can just give it to the amplitudes people, and you guys know now like interesting features of amplitude, so that you can kind of reap the rewards of like tell me how amplitudes will behave if I do this transform, right? So what I do want to point out, and what we're going to get to at the very end, like notice this is transforming scattering at all energy scales. So if this were just an S matrix element from the point of view of an effective field theory, this is going to be fine. But if you're studying scattering as this abstract object, or you can make some sort of statements about features of this amplitude, then you can also make similar statements about features of this transformed amplitude. So the way that we're going to go about the rest of these lectures is that we're going to talk about these UV issues at the end. But in the meantime, we're going to be able to show that I can do this, like parts of this transform on parts of this amplitude to study soft limits, to study collinear limits here. And so it's kind of like, I would say that it's good examples for then just how to repeat that to whatever your favorite feature of amplitudes is, and you can probably write a nice paper on that. So just pointing that out there, there's a lot of people who care about these objects and a lot of people who know about these objects, so invitation. Great. So, and they're not the same people. The Taylor group is pretty good, but yeah. So just as a plug there. Great. So, and also you can see like the paper by Nima et al. Like really did say some very nice things by starting to. So, what we have is the following: is we have now not only that. So this is our construction here, and what we have is we have also the following statement that I'm going to use as my starting point to talk about soft limits. So our next section is going to be about soft limits. And what I want to point out is that before we knew what a soft limit was, we knew that a soft limit was energy equals to 0. So now one might be slightly confused is, okay, I have this guy which is transforming over all energy. So this is omega I, let's be careful there. If I send one of the energies to 0, that's great, but I need to integrate over all energies. What do I do? So the point will be to try to extract how this soft limit gets encoded in the function of delta here. So don't be worried about the fact that I don't know, like this guy only contributes some part of this transform. We'll be able to see that it contributes a very distinct feature in delta here. Great. So let me kind of go back through that. So the way that I would maybe, like, I'm a bit biased towards this asymptotic symmetry and the wave function side of things. So if I were just going to try to say, I'm going to only look at the external set areas, can I actually guess where the delta are going to be? I actually can. And so maybe that's kind of cute. So the way that one would guess it without having to do the work is the following, is that, say all I know instead of about soft theorems is about asymptotic symmetries, then I also know that the operators that I've constructed, so I know how to, I basically know the first couple chapters of Weinberg, and I know the asymptotic symmetry story, but I don't know the section on soft theorems. What would I get? I would get that, okay, I have my operator here, and it will, the commutator with my local field operator is going to generate a shift along the wave function that I use to define that operator. So essentially what one can think about is that this guy is extracting the symplectic partner of itself in the definition. So great, let me write that down. Okay. So if I started from this definition, this guy is basically extracting a symplectic partner here. So that symplectic partner will shift the operator by this guy again, up to the fact that there's complex conjugations occurring. So what this is going to do is it's going to give me the following shift. And right, so this operator is a local operator function of X. So this guy depends on X and W again. So what I have right now is I have an operator that's defined in my 4D Hilbert space, but effectively it's supposed to be a local operator in my 2D guy, which taking a local operator in 4D, so maybe I'll make that X more explicit here, it will generate a shift in that guy. So yesterday when we were talking about these soft theorems, basically we paid a lot of attention to the part of the asymptotic symmetry charge that was just linear in the metric mode. So the kind of fun thing about that is that all of these issues of like non-integrability of your charges kind of goes away when you're looking at what is this like basically just the part that does the inhomogeneous shift. So it makes your life easier from the point of view of the canonical GR side of things too. So all I'm really doing right now is literally taking the free mode expansion here, taking it like and using that algebra and seeing that with the wave functions that I've constructed, I shift my guy here. So these, and again, everything's modular gauge equivalent, so we don't be worried about that, but let's not worry about that here. So what we have right now is that this is a wave function in my space-time. These are all primaries. Can I find some values of delta and J so that this guy is pure gauge? And if it is pure gauge, and it also doesn't fall off funny, like basically makes it to infinity, then I can look at its large R expansion. So like, let's look at this. Like, so first we ask, when is this pure gauge? And the second thing we ask is like, how does it behave at large R? And then what one finds is that, okay, so for J equals 1, I have delta equals 1, and this corresponds to a large U1 gauge charge. For J equals 2, I find 2 values of delta for which the Mellin transform guide, so basically the one that is like there are 2 options for the wave function. So the one that is gauge equivalent to the Mellin transform is only 2 values of delta. So delta equals 1 is a super translation. And delta equals 0 is a super rotation. This actually is a diff S2, but it's shadowed to a super rotation. So this is called diff S2. 2. So, okay. So what I want to say about here is, so what I've done here is all I've done is I know this transformation has to basically be true up to gauge equivalence. This guy here is for certain values of fixed values. So this is, I'm looking only at the right-hand side of this object here. So this guy here, if I plug in fixed spin, I will only find a certain discrete number of delta for which the guy that is this conformal primary wave function, which is essentially is a gauge choice, also is large gauge. So what I mean to say is the following. So I say that delta, I say that my value of J that I want everything to transform under maps or is equal to the value of the spin. So absolute value of J equals spin is basically that combined with the fact that its conformal primary wave function is effectively a gauge choice. So in some sense, that's like the first step of our asymptotic symmetry analysis. I've made a gauge choice, but then within that gauge fixing, there's still some values of delta at which it becomes pure gauge. And that's what I'm looking at for here. So for special values of delta, this guy literally is pure gauge, but there's only a finite number. And then I look at how that wave function behaves at large R, and I can see that for the U1 case, it's pure gauge and it's a order 1 at infinity gauge transformation. So this is a large U1 gauge transformation. And so let me put large here. And then for spin 2, there's a super translation. If you take delta to 1 and delta is 0, you can see that it's diff S2. So you can literally look at the larger element and identify that. And you can also find for spin 3/2 the analog, which is a large SUSY transformation. And ideally, I mean, you could go up to higher spin even if it's not a consistent theory, and you can like it would be a longer and longer list of pure gauge guys. So that's kind of nice from the point of view of like literally, if I try to avoid amplitudes as much as possible, I can still like identify that, okay, there should be some special aesthetic symmetries of these values of delta and J. So then I get to remember this Weinberg story and the connections by Strominger and others about the fact that a asymptotic symmetry corresponds to a soft theorem. So if I do that in the momentum space basis, then I knew that these asymptotic symmetries corresponded to certain soft theorems. So now I'm going to say that, okay, in any other basis, well, my conformal primaries are a basis. I have these asymptotic symmetries of these certain values of delta, so they should correspond to the conformally soft theorems. Like that's my guess, I guess. And so one can actually show that this is indeed correct. And one sees this as follows. So let me write down my S matrix. And right now I'm going to be expanding in the value of one of the energies. So I think, yeah.
I may have a dumb question.
Oh, no, please.
But if I imagine of taking a Poincare transformation, like a translation,
exactly
in the Mellin transform, there I know that I have basically a shift which depends on the energy.
Yes.
Which then it should correspond to a shift in the conformal dimension, right?
Exactly. Yes.
But wouldn't this imply that basically all the integers that we could write should be the same? Like
no. Okay. So basically, you get non-trivial relations to okay. So what you're going to find at one point in the lecture notes, I think like a little bit later, and maybe it's in this section or not, is that there's a word identity for the amplitude corresponding to shifting the weights. So acting with a translation on the wave function is one wants to be a little bit careful. So the reason why I say I want to be careful is that basically, right, like when you actually do a so let's just do this translation. I do, sorry, d by dx mu of 1 over negative q dot x to the delta. And that will give me like, wait, there was some delta, like basically I'm not gonna like screw that up live. But so it's negative delta negative q mu over negative q dot x. Okay, so this guy now has this q mu sitting here. So one should be a little bit, how do I want to say this? Okay, so we know that, okay, so basically what I'm trying to say is that it's true that you can see that it shifts, like definitely shifts the weights. The way that I like to think about it though is I would normally break down my translation generators into an index like guy here. And so then like each of the translation generators has a SL2C weight that it's basically moving you around. So like what I basically want to say is that it's not, the translations don't actually preserve the celestial sphere, right? They're moving you off the celestial sphere. So I think there's a better sense in which you would say that the translations aren't quite like, I don't want to say linearly, they're obviously linearly realized in the Hilbert space, but like it's not like it's, I would not go in so far as to saying that like you can't distinguish different values of delta because it shifts. Like it's not like it always takes you.
Maybe if I can have a comment, like if you use the soft theorem, you can see that these values of delta come from the pole. And the S matrix is coordinate invariant. So I mean, that's in momentum space is 1 over omega.
Yeah. So sorry. I think that the issue is that like, okay, so yeah. So depending on what your question is trying to get at, like I want to point out that basically you can see that it's a different constraint. I agree with you that like you can look at these soft theorems and their commutators and stuff like that and find consistency conditions for like how to shift the weights. Like we'll see that the subletting soft theorem like basically shifts the weight down, and you can use that with the other soft theorems and somehow like find more consistency conditions on the amplitudes. So everything I'm saying here doesn't invalidate the wave functions themselves transforming a certain way in what I've identified. The translations will, however, give you non-trivial constraints on the amplitudes because basically the weight of each external state is shifted, but then the sum of them is what has to vanish, not like that like it's equivalent to scattering. So what I'm going to say, so here's the difference. Like I think what you were saying sounded like you were saying that a delta plus 1 delta, like so this is delta 1 delta 2 dot is a delta 1. You know, that's not true. What's true is that the sum over the shifted for each of them is 0. So like maybe I misheard your question. I'm happy to talk about it more. Is that kind of what the like? Sorry.
Okay, this kind of basically fixing a gauge for which delta equals to 0 equal. I mean, my question was
no, like I'm saying that like it's like right. You see how this? Okay, sorry. What I'm trying to point out is that basically, even though on the single particle states, you can see that the action of translations will effectively give you the amplitude with the shifted weight. It's times q mu. It's not like it takes the wave function to the wave function plus delta. You can see that even here, right? Mm-hmm. So, right. So this has now bulk spin that's changed, right? So this won't be. If you wanted to look at what is this wave function from the like let's look at this object from the point of view of what I was constructing earlier. We see it's this guy doesn't change the W dependence. So basically, the issue now is its representation S is now corresponding to spin 1, but its J is still 0, and you can see that here. So everything that I've been talking about here is looking at the values of right now J absolute value equals S. So from the point of view of the wave function story, translations don't just shift the weight. So one should be careful about that. Okay.
Okay.
Yeah.
Thank you.
Yeah. Nice. Yeah. From the amplitudes they do. So because it's basically, so like, you know, like when you have a transformation and you have like, yeah, like it's basically the same thing as if you take the polarization vectors times the state, and then you shift the polarization vector by q mu. Like the relation that you're getting isn't just that it's you have to be able to extract that q mu out of it. So it does effectively give you this for the amplitudes, but one needs to be wary of that. Okay, so good. Okay, so let me now point out the following. So as Ricardo was saying, we're going to see that this indeed is a soft theorem. So like the thing that I'm advertising here does bear out in the amplitude as follows. So I'm going to use the shorthand A to denote my S matrix in momentum space. Okay, so sorry, this is the definition here. I'm expanding it in one of the energies. So this is like the energy of one gauge boson. So, and by gauge particle, I'm kind of like grouping gravity with it. So I know from the Weinberg and Lowe and other soft theorem studies that essentially this guy will have a pole and then it'll have an ordered one piece, yada, yada here. If I look at how these coefficients give you something in the conformal basis, we'll see the following. So the first kind of very naive thing to just kind of, so Chung and others basically pointed this out, is that if I put some cutoff and I do my energy integral and I do it to some power of the energy also, then I'm going to get a pole as follows. So right now, this isn't going to be very satisfactory, but it will indicate kind of what we want to look for. So all I'm saying is that, okay, so I'm looking at scattering, I'm looking at the very deep infrared. I don't really know how the UV behavior is going to be. And especially from the point of view of soft theorems, I shouldn't have had to rely on like a UV complete theory of gravity or whatever. So what I'm doing right now is I'm just showing that in the deep IR limit, that Mellin transform is picking up essentially something that will contribute a pull in delta. So what I would naively then be looking for from just this integral here is how can I guarantee that I will basically try to say that when I do this Mellin transform, I actually literally am selecting out the residue of this pull in delta. So right now with this lambda here, this kind of looks arbitrary, but we'll be able to next show a set of manipulations so that we can see that the residue of the celestial amplitude at a given value of delta is going to give me the corresponding conformal soft theorem. So that's going to be good. So let us see that happen. So we're going to say that the limit as delta goes to negative n of delta plus n, integral from 0 to infinity d omega to the delta minus 1 of a power series expansion right now. K is a n. So the way that one can show this is one uses the following distributional identity. And this particular version is written in the, like I think Anna Reclariu and Pate et al. Paper, but also Guevara and like Poom and others have studied soft limits, similarly Taylor. So we use this relation to basically show that, okay, so the delta is going to negative n, so that's where this epsilon is coming appearing here. And then you can check that this should pick out the particular value of like the particular mode in this expansion in low frequencies here. So basically what's happening is that when I do this Mellin transform, every soft theorem is appearing as a residue of a pull in delta. And moreover, when I have, but I know, for instance, that when I'm doing that transform, that amplitude is basically of the external state for that is my wave function with the value of delta here up to gauge equivalence. So what I have right now is essentially kind of the proof from the amplitude side of things that indeed the values of delta that I was pointing out over here correspond to the soft theorem. So okay. So from my point of view, where I'm just looking at wave functions, I told you, okay, I plug in delta equals 1 for gravity. And I look at large R and I tell you that's a super translation. Then I go back to yesterday's lecture and I say super translations correspond to the leading soft theorem in Weinberg's like a paper. So now let's check that. So I see that as delta goes to 1, which is what I was saying here, then I pick out
frozen again.
Okay, good. Okay, so as delta equals 1, I pick out A1, and that was the pole here that was Weinberg's. Okay, next thing I said was gravity. Subleading soft theorem in gravity gave me this stress tensor, which is the shadow relation here. So I have to write an integral transform over the celestial sphere, but the operator that I was selecting is this delta equals 0 guy. So now I go over here and I see, look, okay, so n equals 0. Oh no. Okay. It's still frozen. No.
No.
Good. Okay. So all I was doing was basically, so let's make sure I can do this. Okay. I'm looking here. I'm pointing out that my guesses were right. so this is like, I know that these guys are pure gauge. I know what transformations they correspond to. So delta equals 0 indeed is this subleading soft theorem. So everything checks out, which is good. But from the point of view of Amplitudes person, this would be the more like the proof that this soft theorem, this conformally soft theorem is at a certain value of delta. So this proof is that the conformal soft theorems map onto the soft theorems that you know from momentum space. And then this version of it is telling you, so say you did this first. So you're like, okay, I found these soft theorems. Then I found these values of delta. Let's look at the wave functions for those values of delta and check, yes, they are those large gauge transformations. So like that's the route you would do, like that I guess like my route versus the people who derive these soft theorems route would be the other way up. So it's nice that it's all consistent. So that's good. And the consistency there is that, of course, we know what these guys are because that was starting our story. So we knew that the leading soft graviton theorem was telling me that there was some super translation symmetry in the bulk. We knew the subleading guy corresponded to the stress tensor and the super rotations. And the kind of validating thing is that we can go full swing and see how the conformal basis versions of these appear. So that's kind of nice.
Maybe just a comment, you're working at 3 level here for the amplitude.
We are, but we're not really. Okay, so what I mean to say is that everything I've done, everything that I've shown you has been 3 level, but it's because it's the easiest way to do it. There is also, so basically the leading soft theorem doesn't get loop correction, so that holds. The subleading soft theorem gets a 1 loop exact correction, and then there's still a modified stress tensor for which it holds. So from that point of view, then the values, like this transform should be able to be done to the full guy, and then I think it's fine. I mean, maybe I think that you're right that maybe one, like I could imagine.
I was thinking about the log of omega term also.
Yeah. No. Yeah. There's log. No. Yeah. No. Sorry. Everything. Sorry. No, let me get there. So this is true at the level of this expansion is only valid at 3 level. Sure. This statement is beyond. So what happens is that when you have a log here, you get multiple poles. So what's going to happen is that at delta equals 0, you have a like double pole, and like the residue is still true. So all the statement I'm making about the residue is still true, and then with Andrea, hopefully we'll finish just like write it out. That all of the logs you're getting there are just different. Like it's basically the single particle version of what's in Nema's paper. That you have higher order poles at a given value of delta. So what I'm saying is, sorry, I'm telling you statements that are true beyond 3 level, but I obviously wrote down an expansion that's only true at 3 level. So yeah, great. Good. Yeah.
Question. Okay. I can imagine of having, I don't know, perhaps a sub-leading soft theorem and sub-leading and so on. So I don't know if one could go on infinitely, like too many orders, but wouldn't I expect like an infinite amount of generators that
yes,
like
and so that's what I'm going to get into. That's actually where I'm going to go right now. If you look, so let me see if this thing's scrolling. Let me scroll. Okay, so what I want to point out is the following. So if you recall so depending on your familiarity with the literature at the time, basically like a look at, so Compiglia and Latta went into a lot of effort to try to find like a large gauge symmetry interpretation of the other soft theorem. So the soft theorems that I focus on right now and that I wrote down corresponding to these values of delta, these guys are all like the soft theorems that are universal. Like this guy has a 1 loop exact correction and it's fine. So all of these are like legit not going to go away in the full theory. I don't want to then say the other ones are going to go away. let me not say that. Definitely like this infinite tower of things you see in self-dual gravity. I don't know if I want to say that they're not correct, whatever. Like I'm not going to say anything more than that. These guys are the ones that nobody's bothering about the loop corrections for it. The ones that people are like Freddie might say one thing, like the one wizard, there's some conflict on the loop corrections, have kind of sketchier asymptotic symmetry interpretations. Now, I don't want to go, okay, when I say sketchier, I want to be careful because basically I think it's reasonable. Like, so for instance, there's ways to find some overleading gauge transformation that will select out the mode that then becomes the soft theorem, et cetera. Like you can mechanically find gauge transformation. Those guys somehow are not consistent with the conformal primary gauge. So I would say that it's still a little bit open about how to necessarily have a very clean, like this, because everything here is modulo gauge equivalence, it's not, because I don't have values of delta J for which the guy is pure gauge, I'm not like forced to not have like a soft theorem there or something like that. It's not like the direction is only one way. It's an implication, not equivalence. So what we were looking for essentially is to try to make sure that we could incorporate all of these special values of delta, where you can have effectively soft theorems at least to some loop order, or so like valid at tree level at least, or in special theories. And so right now I'm going to present a way to basically identify all of those guys that you're seeing in these nice papers recently by Andy and Guevara and Pete and others. So the way to do that is, instead of looking at the values of delta for which is pure gauge, you look at the values of delta for which there are primary descendants. And these guys are all included in that. But the asymptotic symmetry interpretation is less obvious there, in the same way that the asymptotic symmetry interpretation for the soft theorem I would say is also less obvious there. Because they're slightly, like the charges are divergent, and then you have to subtract off the lead. I mean, there's a lot of little, there's obviously something there that can be tied nicer, but I'm going to present a route that does include all of those at least. And like you can play with them. So the way that I'm going to do that is as follows. So because we spent some time to guarantee that these operators behaved in the appropriate SL2C covariant way, what I have is the following. As I have now, I know what these operators L and -1 are from the point of view of 4D Hilbert space. And just using the algebra, so the duet algebra, I have the following. I guess this is just SL2C, sorry. Don't even need to be that fancy. 2L0 plus K minus 1. And then that tells me that if I have a primary state, then I will have a null state at special values of the weight. Great. So the statement here is the following. So this is just algebra. And if I wanted to not deal with state operator correspondences, I can literally replace this with like W derivatives in the end. So the thing that I'm saying right now is that basically, if this vanishes, so if H equals 1/2 1 minus K, where K is then in positive integers, then I will see that if I start with a wave function and then I take its descendants, so I literally take dW to the K of my my primary operator, then that guy is also going to be a primary for special values of K. So what happens is the following, is that when this also is true for K bar, so the L bar basically, I have a nested set of primary descendants. So this guy has 1 minus K over 2, 1 minus K bar over 2, and then I basically do L bar to the -1 to the K bar, and then I do L -1 to the K. So what's happening here is that basically I have my primaries, and I actually have radiative primaries, and I can take derivatives of them, and I can also sometimes land on other primaries. What I will end up seeing is the following nice structure. So, okay, I don't know if I think I didn't show this. I said it kind of at the next section, but let me just say it right now because I think it's kind of nice given the questions. So let's look at the case of the leading and the subleading graviton. Okay, so the value delta equals 1 was supposed to correspond to the leading guy, and the value delta equals 0 was supposed to go into the, okay, so I didn't align it very well. Let me try to align them better vertically so you can actually see the picture. Okay, so vaguely, Okay, it's a little shitty. But so what I want to say is the following. So this is j equals -2. This is j equals +2. This operator here and this operator here are the soft theorems. They have primary descendants, which have delta equals 0 and j, oh, sorry, delta, not 0, j equals 0, sorry. J equals 0. So it's 1, 2 down. And then 1 plus 1 plus 1 is delta equals 3. This guy also has delta equals 3, even though it's drawn pretty shitty. This has j equals +1. This is j equals -1. This is delta equals 2. This is the stress tensor. And j equals +2. Okay, so typically, I guess I wouldn't have gone into this because it's a little bit of a distraction, but because the questions, it seems like appropriate to do. When I'm on the radiator, so basically when I'm along the locus here or here, I'm at a negative helicity or positive helicity soft theorem. So what happens is you'll see that the leading soft theorems have a helicity degeneracy. If you take the shadow of the negative helicity soft theorem, you get the positive helicity and vice versa. And that's just captured by the fact that they both descend to the same operator here. The guy up here, its symplectic partner is addressing mode, but we don't need to go into that today. For the stress tensor here, it was an integral convolution of the guy over here. They both descend to a guy at delta equals 3 down here. What's happening, which is slightly nice, is that you have, these are the soft parts, and in the constraint equations, you have another hard operator. The hard operator is a primary sitting down here. So the soft operator is at the bottom. It's a descendant of radiative guys. The hard operator is also at this gate, but it's not a descendant. And so you have a relation between primary descendants and other primaries that vanishes. And so that, I guess, null type relation is the word identities that you have. So with that picture, that's going to explain how we get these extra global symmetries that correspond to like the subleading soft graviton, because this picture can extend to the other, like this is for the ones where there are gauge transformations. So what happens, okay, so in the case where there's gauge symmetries, basically there's a top to this diamond. So I have radiative modes that have a symplectic partner where there's a gauge mode at the top that is symplectically paired to these guys. To basically this guy for the other diamond is paired to the charge here at the bottom. For the other values where they're null states, so for instance, the most subleading soft graviton theorem, it looks like the following. It looks like I'm going from the delta equals -1 guy down to the delta equals 3 guy. That's basically 4 derivatives down. So what I have here now is basically it descends to its own shadow. This is a soft theorem here, and then like this guy, if I take those derivatives of the soft operator, it's going to be local in the matter field. So the hard charge guy is sitting here. So when I have this structure, you can see that there isn't kind of like this pure gauge guy sitting here. So maybe very roughly speaking, like maybe this is actually a hint that I can understand that a little bit better. Definitely mechanically, I can get all the soft theorems with this set of primary descendants. And so what will happen is if I go up for the infinite values of delta, so basically all of these, right? So H is -1/2, 1 minus K. So K can be infinitely negative right now, and I'm going to have primary descendants. The thing that happens there is the following. So if I go right one step above this, so the first soft theorem that's, okay, so leading gravity, subleading gravity, subleading gravity. Next one, which is the first start of the infinite tower, has a funny property as follows. So what I have is I have basically, I'm always starting at j equals ±2. And then I can find that there are two sets of primary descendants, and they come back together. But the funny thing about it is that each of these guys actually vanish. So what's different here is essentially like I'm on the left corner of the diamond, I'm on versus the top corner of the diamond. So the reason, okay, so when I say about that, so I guess I'm gonna get like lose people except for the ones that was asking the question. So what's happening right here though is that I don't have a primary descendant. That's non-trivial right now. So like this guy at the bottom here is the soft charge, which then plus the hard charge is the word identity. This guy is just 0. So little bit wary of how to interpret that. Basically, there's this nice, like you have compare and others talking about multiples. Basically, the values of delta would point out that maybe it should be these guys, but you have this kind of funny statement where like it's not clear that there are extra soft charges because it just descends to 0 here. So I think that there's ingredients pointing to a picture that's going to probably be clear within the next year of exactly like just a very clean, like hopefully statement about it. But you can see the differences at least. And it's basically because you're going from a diamond where you're the left corner and there's like a guy at the top that is addressing, to one where you're at the top corner and there's nothing below it. So it's a kind of the same algebra. So naturally then like this, the kind of series expanding gives you the same types of, okay, they're primary senses and levels. It's great. They always have primary sense for these guys, but the nature of them is different, distinctly different here. So hopefully that aside is helpful to whoever actually asked that question, and then hopefully not too distracting for the rest of you guys. So thanks. Yeah. Good. Okay.
Okay.
Okay. So how am I doing on time?
It's actually over.
Oh no. Okay, good. That's okay. Honestly, that's fine because I think the next. Yeah. Sorry. Okay.
Do you want to say?
I'm really happy that I'm getting into amplitudes and you guys are asking questions. So I'm like, this is fun for me at least. So,
okay. So let's see if there are some questions.
I'm gonna mark where I left off. Great.
Well, I don't know, maybe I'll ask one. So the relation between these two conformal modes or different helicity, I guess it's related also to double counting on the soft modes, right, in the phase space. There was a phase space issue of the double counting of soft modes. I guess it's the same issue that the two are related?
Yes.
Okay.
So, yeah. So what I want to say is that it's only an issue for the leading bosonic soft theorems, because as you can see, this guy and it's reflected is the other soft theorem. So that guy
there was a factor 1/2 in the gauge transformation on the right hand side, right? So if I remember correctly, of the charges, like and there was, you need to extend a little the phase space, and because of this relation between the soft modes.
Okay, yes. So there's different halves. There's a half coming from the positive frequency limit that I think is there even for these other guys. There's a half that's coming from there's a lack of independence in this independence of the two modes. I agree from the most of the funny thing about it, and I want to share Lucas' analogies. Like in principle, right? Like one should be able to tell from like starting from the representation theory for the two helicity little group, like whether or not you're actually independent representations or there's like it's the same one. So I
don't know whether the issue is resolved by going to 2-2 signature or something like that. Like
okay, so if I went to 2-2, it's funny thing what happens in 2-2. So the thing that's happening here is each of these guys, the shadow transforms are Weil reflections, so the light transforms are Weil reflections separately in one or the other. So you can get similar descendancy structures there. In 2-2, I still would say like formally I think that these things would still close, because this is like what I'm trying to say about that is if I just wrote down the wave function, then like I'm taking derivatives and I can see that like there is even though W and W bar are independent real variables, it doesn't affect the fact that the derivatives commute with each other. So that stuff.
Okay.
Yeah. But the thing that you don't have necessarily, I think the in and out in 2-2 changes. So there's a half coming from selecting in and out modes. And I think that depending on how you treat you can. So there's something there, but I don't think it's going to affect the W and W bar representations, because what I would say is, okay, so you say this guy, I think I would still say there's an operator at the top here. And that if you, okay, yes, W and W bar on complex conjugate. So in 2-2, you look like, oh, that's special. But if I said that there's some guy at the top that exists, there's an operator in your theory. So I say that so I think this gets into a question of the phase space for the spontaneous symmetry breaking modes. And so that should be a separate, like conformally soft CFT that has its own kind of ways to compute it just internally, I think. And for that, I would recommend the IR, like it's coming off of the IR part of the paper by Nima et al. And like this vertex separated things there. But so what I want to say is if I said that there's an O dressing and then there's its symplectic partner. So there's a funny too in the CFT picture where somehow like I think we haven't quite understood how to deal with the symplectic partner as opposed to the mode. But if I just say that this guy, then if I take two W derivatives of this O symplectic partner, is equal to my h equals 1/2 h bar equals, or whatever. I don't want to say that down there, but 3/2, something like that. I mean, did that wrong. Okay, so whatever, if I screwed that up, but so what I'm saying is that basically, if I say this is true, and then I have the other guy, which is dw bar squared of that O-symplectic partner, then I'm still going to have that redundancy in the helicity relations, because I'm going to just see that dw squared, dw bar squared of OSP is the O soft at the bottom. So I don't think that changing signature is going to change that. But
okay.
But if you know that it has to, then we can revise.
No. It was a question. That's why.
No, I don't think it does. I think it will resolve some in and out things, but not that.
Okay. I don't see any other questions. So yeah, I invite everyone to come to the tutorial, and yeah, for the moment we close it here and we reconvene at in 25 minutes, more or less. Okay.
Thank you, guys.
Thank you, Sabrina.